Are we ready? Well, welcome to the Kent seminar series up here this semester. We're still trying to fill out the speaking list, so if for some reason you didn't volunteer yet, you may be volunteered. And if you don't volunteer, we have spaces all throughout the semester. Next week, Pen Cheng just got volunteered to speak next week on GPR. This week we have Adam Beach talking about low temperature cracking on recycled asphalt shingle binder or mixes?
I'm just going to talk about
binder. And Adam's been here, I think, almost 2 years.
Yeah.
And from Michigan State, we got a bachelor's degree, so let's welcome Adam to this.
Thanks, Professor Raisler. As he said, my focus here at Illinois is on the RAS. Today I'm just going to focus on the binder testing that I've done and maybe give a little bit of an intro into some of the performance testing I hope to do. Let's see if we can. This is an outline of my presentation. I'm going to give a quick introduction and background on new asphalt roofing shingles because I think it's important to understand the components of them in order to, when we consider the fact that when we're going to include them in hot mix asphalt. And then I'm going to get into some of the recycling, and this project actually that I'm on is funded by the OMP, the O'Hare Modernization Program. And I'm going to talk about some of the climate analysis that we did because they're the ones that originally wanted to use the RAS. And then I'm going to talk about some of the binder testing that I've done, binder characterization, specifically at the low temperatures, because that's what we're focused on. Okay, so asphalt roofing shingles. It's a basic list of the composition of them. You have a weathered grade asphalt, and this asphalt is quite a bit different than the asphalt that we include in pavements. It's quite a bit stiffer, and it's very unique in that aspect, and there's quite a bit more of it actually when you consider relative percentages. I'll get into that later. We have a roofing felt that provides the basic backing that provides almost like a structure for the shingle, and we have two different types of roofing felts that we can use. We have an organic type, which is essentially a wood or cellulose base, and then you have fiberglass. And then I have a little asterisk there next to asbestos. Since we're considering that we're going to possibly recycle these things, the fiberglass, for a while there they did use asbestos for use in as the fiberglass in the fiberglass. So that's important to keep in mind when we're reclaiming these things. We also have mineral fillers, which provide some of the structure support there, and then the sand granulars actually is on the top of the shingle, and that's there for aesthetics. That provides the color that you see on the shingles on the houses. And then we have a backing dust that is used primarily to prevent the shingles from sticking together when they're transported. When we talk about relative percentages of these components in the shingles, I have two different pie charts here, which basically we have two different types of shingles, as I mentioned, the organic and the fiberglass, and you have different percentages of these relative components for each of these types of shingles. Generally speaking, there's a higher asphalt content in the organic shingles as opposed to fiberglass shingles. So I think this is important to know because when we talk about reclaiming these shingles off the roofs of houses, which I'm going to get into further in a second here, but when we're talking about reclaiming these things, it's important to understand, whether or not we're getting an organic shingle or a fiberglass shingle, because that can impact the properties of the mixture, of the asphalt mixture. Okay, so part of the idea here is that there's a lot of excess shingles that are being generated from the manufacturing process, as well as torn off shingles from the roofs of old houses. When we talk about the manufacturing process, there's a lot of leftover shingles from these plants, And primarily this is shingles that, for whatever reason they didn't meet the specification. So instead of dumping them in the landfill, it's more economically feasible for both parties to bring it to a processing facility. Same thing with the post-consumer, and these are actually from old houses where they tear them off. So these have had their life cycle, and they've been aged on the roofs of old houses. One thing I want to note here is that, let's see if this works. There we go. One thing I want to note here is that there's quite a bit more post-consumer shingles nowadays because they're replacing these roofs quite frequently. So that's the primary source of our shingles when we're talking about recycling them. There's a picture of some tear-off shingles. He's ripping them off the houses. As you can see, you get quite a lot of debris when you tear them off the houses. You get I've seen pieces of glass and other things. I mean, they'll bring all kinds of stuff to the processing facility. That's important to keep in mind when we're talking about putting it in the asphalt mixture. This is shingle waste from a manufacturing facility. So when we talk about putting it in the HMA, well, one of the questions is there any benefits? Well, there are some benefits. Primarily, the one benefit is that we're reducing consumption of virgin materials. Essentially, what you're doing is you're taking a certain portion of the virgin asphalt binder content and replacing it with the binder of the asphalt shingle. You have some sustainability benefits like reduced emissions and reduced disposal in landfills. It's actually cheaper for these people, for the people that tear these shingles off the roofs of houses. It's cheaper for them to actually bring them to a processing facility as opposed to the landfill. The processing facility charges them less because they are charged when they bring the shingle to these places. And then you have improved public perception, and most importantly, I think it's critical, is the fact that you have improved economic competitiveness. There is a certain economic incentive for including these things in hot mix asphalt and replacing some of that virgin binder content because these are significantly cheaper. I talked about the processing facility. We here in Illinois, one of our main producers is Southwind RAS. They're fairly new. They've been around here only about 2 or 3 years. And what they do is first they have to go through an inspection because there can be up to 20% of debris and other things in the stuff that they get. What they do is they inspect it, they clean it off, they use actually a huge magnet that can pick up all the metal out of the shingle, and then they grind it through. They have multiple grinders, and they try to grind it as fine as possible. We say less than 3/8 inch, which is pretty fine, so therefore you can get more of that binder off the shingle. All right, so that's basics behind the recycling of asphalt shingles. I mentioned that this project is through O'Hare, and one of our initial goals here was to figure out, well, how can we include this RAS in the airport runway? And one of the first ideas was to include this in an asphalt treated permeable base. Many of you here are familiar with that. Essentially, it's a drainage layer, and it provides no structural support. But the primary issue is that there is a problem with the construction with these ATPB layers, and the fact that what they do is they have to pave it, and because it has such a high air void content, they have to basically wait 6 or 7 hours to pave the next layer because there's not any support there for the paver. And so that's delayed, that's delayed time, that's wasting money in a sense. So one of the ideas was if we include RAS in this ATPB mix, then because RAS is a stiffer material, generally speaking, and it also contains fibers, that it might reduce that waiting time, and it will therefore provide more structural support, and you don't have to wait for it to cool down as long, and the crews can get on there quicker. So the question that was posed to us here at Illinois is, what percentage of RAS can be added such that significant thermal stresses do not build up? The issue that we were concerned with is the low temperature side. I pointed out here that it has a high PG grade. Generally speaking, with these recycled materials, the binder is stiffer. So you usually get improvement on, on the high temperature side, and you'll have reduced rutting and things like that. But on the low temperature side, it might create problems like cracking. So that was the issue that we were focused on. Okay, so I'm going to go through some of the climate analysis that we did. This is a look at one of the runways that we were analyzing. You have 17 inches of PCC, and then you have a dense graded asphalt, and underneath that we have the ATPB layer, which was the layer that we were concerned with. We were looking at the temperatures that would occur at this location, so about 23 inches underneath the pavement. And we use the Enhanced Integrated Climate Model, which is the model that they use with MEPDG, and to look at temperature variations throughout the year. We looked at 2000 and 2001 here, I believe, and you can see the general temperature variations on the surface, and then we were looking at 23 inches, 23-inch depth, so about right here. As you can see, there's quite a bit less fluctuation of temperature. So that's important to keep in mind when we're talking about, thermal-induced stresses in the pavement. So if we look at this temperature variation at that depth throughout the year, we can see, this is at 23 inches, we can see that we get the lowest temperature about right here. If we zoom in, that temperature happens to be minus 2.4 C. So that kind of gives us an idea of what we should expect, for temperatures there. And also, when we think about binders, we think about, Illinois, here in Illinois, 64 minus 22 binder is quite common. And that low temperature is minus 22 degrees C on the binder. So, I mean, this is quite a bit higher than what would be expected, than what we would, the minimum possible temperature that we would expect before cracking would occur from a 64 minus 22 binder. So, relatively speaking, that's not a very high temperature, or that's not a very low temperature, rather. So, using that temperature, we did some preliminary estimates. They wanted to get this thing rolling as quickly as possible. The idea came up in mid-June, and they were actually throwing this stuff on the runway by the beginning of the fall. So we did some preliminary analysis with the EICM, and then what we quickly did was ran some acoustic emission tests on the binder, and I'm not going to get into too much, but essentially this embrittlement temperature is the temperature at which microcracking starts to occur. And so that was kind of an odd result that we were getting such a low temperature here. I mean, the RAS, because it's so stiff, you would expect it to possibly start cracking at closer to 0 C as opposed to minus 16 C. But when we talk about reasoning, the fact that if we include RAS in the ATPB layer, the predicted temperature was minus 2.4 C, and so if we include the implication is that the effective superpave asphalt binder grade should be less than minus 2.4 C. So when we have a version PG 64 minus 22, and we replace some of that with a RAS binder, we kind of expected that the effective binder grade would still remain below this minus 2.4 C, and we expected that maybe 50 to 60% binder replacement would be acceptable. And so they went ahead with that. That provided enough reasoning to move ahead with the ATPB without and assume no cracking would occur. So the next step then became, if we include this in the ATPB mixture, that's fine, but what happens if we were to include RAS in a surface mixture, somewhere where we have significantly more temperature fluctuations, and we might have some thermal cracking, and basically you're more susceptible to these kinds of distresses. And so the next step was to go through a thorough PG binder characterization especially on the low temperature end. And I'm going to go through that quickly. First off, I ran an extraction recovery on the recycled asphalt shingle to just obtain the binder alone. And I attempted to run some BBR tests on the extracted shingle binder. I say attempted because I really wasn't successful. This stuff is such a unique material, and it's so stiff in many respects that you cannot, either at the higher temperatures it deflected too much below that 5 millimeter, which is the limit of the machine, or at lower temperatures it broke. So I essentially could not obtain some M values and stiffnesses at some of these temperatures. But in these cases right here, what I did was I reduced the load, so it wasn't within specification, but I think it was pertinent to look at this and to get somewhat of an idea of what we were dealing with. As you can see here, I couldn't get the machine to go any higher temperature than this. This is quite a high temperature. When you're testing PG64 minus 22 binder, you're testing it at minus 12 C. So here we're testing it at 20 C. It's quite a bit different. So I got some values here, and I estimated that the critical M value may be around 28 C. So if we subtract 10 degrees from that, we would estimate maybe a low temperature grade of positive 15 C. And like I said, that's significantly different than traditional asphalt binder that we deal with. But that kind of brought about a more, an idea of, how can we get more of a reasonable idea of what we're dealing with. And the idea came about to do some binder blending. Okay, if we can't evaluate the RAS by itself, maybe we can include the RAS binder in a PG64 minus 22, as a portion of that, and get an idea of what those low temperature grades might be. And we might be able to see a trend. So what I did was I blended it at, I had a virgin percentage, and then I blended at 10%, 20%, and 40% binder. This is by weight of the virgin binder. And I'm going to go through those results quickly. The binder tests that I've ran the BBR already. I'm in the process of running the DSR on these for the high temperature end, and to get some and run some frequency sweeps so we can obtain master curves. And then we're also in the process of running some acoustic emission results on these blended binders as well. So this is a look at the virgin binder. One thing I want to note here, I RTFO aged it, but I did not PAV age it, and that's because if you look at NCHRP 9-12, whenever they included recycled binder, there was little to no difference in the RTFO versus PAV aged binder. And Bonnequist actually came out with a report in 2011 with RAS binder that said essentially the same thing. So that was something I wanted to know. Quickly go through this. We can see the low temperature, the critical temperature right here was minus 14.5, minus 14 for minus 12 for 20% RAS binder. And then it jumps up to minus 9 C for the 40% RAS binder. Keep in mind we have to subtract 10 degrees from this critical temperature, right, to get the low temperature grade. So if we take a look at this holistically, we can see that we got some pretty clear trends here in the fact that this is the blue is the virgin binder, right? And then as we incorporate RAS at these varying percentages, that M value decreases. So basically this M value, I'm assuming you guys are all familiar with this, but essentially what it is the relaxation rate of the binder. It's the ability to relax stresses. And this makes sense. I mean, as you increase the RAS binder, it's stiffer. It can't relax those stresses as easily as a softer PG64 minus 22 binder. So I was pleased with this trend. If we take a look at these low temperature grades, we can see a clear trend here. I was actually quite surprised. This is the M value dominant. I was actually quite surprised in the fact that up to 40% RAS binder, I mean, this temperature is what, 4 or 5 degrees max, maybe 6 degrees. And that's not very much when you consider that at 100% RAS binder, I estimated it maybe around 15 C. So, I mean, maybe we have some kind of exponential function here. I'd like to fill in these extra blending percentages to see, what actually is the case here. But I thought that was interesting. If we take a look at the stiffness, we have two controlling factors: the M value, the relaxation rate of the binder, and then also the stiffness of the binder. And generally speaking, the RAS is a M value dominant binder. So that was the first thing that I looked at. But if we also look at it from a stiffness point of view, what is the stiffness dominant? It's, you get somewhat of a trend. But right here, I had a little anomaly. I wasn't quite sure about that. But when we look at total dominating, if we look at, whether or not the stiffness dominated the PG low temperature grade or the M value dominated the low temperature grade, this is what we get. So this point right here was stiffness dominated, and that's the 0% RAS binder or 100% 64 minus 22. And then as we include RAS binder, all these three are all M value dominated, and this is obviously M value dominated. So that's something to keep in mind. I think as soon as you include this RAS binder, it may not be as stiff, but it cannot relax those stresses for whatever reason. So that was a quick overview of some of my binder testing. Just a quick summary. I think it's a feasible choice to incorporate recycled asphalt shingles in mixtures. One thing that is very important is the fact that the RAS binder, though, is extremely stiff. We saw that with these trends here. And also the concern is also over low temperature susceptibility. Do we have low temperature cracking? I didn't look at this, from a mixture point of view. Regardless of what we get at the binder level, the ultimate question is, can this mix perform in the field? And I think, my plan is to do some low temperature mixture testing to answer this question. But the results from this quick binder study was that if we include up to 40% average binder replacement, it has little to no change in the true PG grade, which was 4 degrees C. So this, I would say, comfortably say that at least at this binder level, from a binder perspective, I think it's acceptable to include that percentage of binder, that binder replacement rather. Acknowledgements, Professor Butler, my supervisor, research group members, and especially the ITT engineers, Jim, especially for help with that rotovap. And then Ross Anderson at the OMP and Southwind RAS for providing me with the RAS material. So that's it. Any questions? Do I have any questions, Slide? No. Sure.
One of your early slides said something about going to 50 to 60% RAS. Do you still intend to do that with your results only going as high as 40%?
That was you're talking about the ATPB slide. Yeah, I mean, I think ideally I'd like to fill this in right here. What we see in the field is that, generally speaking, they don't go above this, about 50% average binder replacement anyways. I mean, the maximum RAS that you typically see is around 5 to 10% by weight of the mixture, and that is about 40% average binder replacement. I think if you wanted to push the envelope, right now we were just verifying that including that 5 to 10% RAS in a surface mixture will be fine. But I think, yeah, if you want to push the envelope, you would need to look at these higher average binder replacements for sure.
Well, that maybe leads into the next question. I know you had tonnages for production bio-waste. Do you know what the current usage is? I mean, are we accumulating a surplus of this waste that is becoming an issue? Or is there not really that much material that we're in a fight to get rid of it?
I know there's quite a bit of material. Like, I talked with Southwind RAS, and they can't even run it all through their production facilities quick enough. They have, like, it's all backed up basically, because it has to go through the inspection process. has to go through all the grinding. They have quite a bit of turnover for the people that they have working there too, and so I mean they can't run it quick enough through. I mean they're constantly using it, so I think there's such a huge supply of it for sure. Yep.
Are there other industries that use this material, like for recycled car stocks or something?
You mean the tear-off shingles?
Yeah.
I'm not aware of any. I mean, I've never heard of any.
All right, so they're only grinding it solely to use in asphalt binder?
Yeah, I'm pretty sure. I mean, I've never heard of it being used anywhere else. I mean, yeah, they haven't told me anything about that, so I'd be surprised if there was. Sure.
I was looking at the slide where they are using 6-inch of over-integrated drainage layer.
Right.
That's really thick, but that's the design issue, I guess, for the O'Hare.
Mm-hmm.
The question is, why would they be concerned about the low temperature cracking in that particular layer, because it's not the structural layer?
Right. The thing is actually they looked at it from also a permeability standpoint, which is obviously the main thing you want from a drainage layer, right? So the thing that we could help them with was the low temperature side, and not to say that there was going to be any cracking anyways. That's why, you know, we kind of gave them the go-ahead, you know, initially with the ATPB layer to say, yeah, there's probably not going to be any cracking or anything down there. Yeah, it doesn't even matter. Right. Right, and that's what I'm saying. We looked at this within a maybe 2-week time period and said, you know, this isn't even critical. So, but the idea is to, you know, eventually get it to a surface mix, and then at that point, you know, that's kind of where we're headed, and that's hopefully where they can get to next year, including it on the surface. Sure.
It's a follow-up. So if you want to ultimately get it to a surface mix, then
Right.
shouldn't your EICM concentrate on the surface level temperature fluctuations and not at 23-inch depth or whatever?
I think, yeah, I mean, I think at the surface, though, you're not looking at, you know, I think you're focused more on that, you know, performance grade. You know, I think that's what the performance grade, super pay performance grade is for the most part. So, you know, when we talk about surface mixtures, we're not concerned about any of the materials underneath. The only thing that's affecting it is the material itself, right? So if you're,
that's what I'm saying. So
yeah.
the temperature value that minus 2.4 or whatever you saw, that was at a depth of
Right.
whatever your layer was, right?
Right.
But should your further analysis not be concentrating on zero, like how the surface fluctuations are?
Yeah, I mean, I guess you could do an analysis based on that, but I think the idea behind SuperPave as a whole is that if we, you know, if we have a PG 64 minus 22 binder, the fact of the matter is if that temperature does not get below that minus 22 period, regardless of where it is in the country, then we won't have an issue. Yeah, I mean, I think if we did run a climate analysis, I can go back to that slide.
Isn't that exactly how that's come up with though? Isn't it based on temperature lines?
It might be, yeah. I think, for example, like the BBR, I think is correlated to a certain cracking potential. It's almost like a empirical value. But yeah, I mean, you could run like an MEPDG type simulation here, using this temperature fluctuation, and get something like that. But I mean, I think, yeah, I mean, I don't know. I mean, I think it's not as critical to look at that, you know, the EICM on the top layer. I think where the EICM is important is when you have layers on top that contribute to that change in temperature fluctuation down below. But
Any other questions? Okay, thanks, Evan.